I'm going to talk about the Yoneda Lemma, and this is joint work with my student Guillaume Boisseau. It's a famous piece of category theory. I'm going to assume none of you know any category theory, so that's my starting assumption. There will be bits of category theory on the slides, but my hope and my expectation is you don't need to understand them if you haven't seen them before. If they don't make any sense, that's perfectly fine. I will be interpreting the category theory as we go, and my point is to try and illustrate this resulting category theory by things that may be more familiar to you, and show that it's not scary. And I'm going to finish off with an application, which was what got Guillaume and me to write this paper, to do with Profunctor Optics, which are basically a fancy way of doing lenses, data accessors, components of data structures. So quite a practical topic, quite a practical conclusion, built on some quite abstract mathematics. So Yoneda was this Japanese mathematician and computer scientist. So he was professor in Tokyo, professor of Theoretical Foundations of Information Science, which is a funny Japanese title, and it's not clear from that what the field is. He was actually a long-standing member of IFIC Working Group 2.1, the group that designed Algol 68, this famous and influential and little-used language, and then went off and spawned a version of it for the Japanese community called Algol N, N for Nippon, which is the Japanese word for Japan. But really, his interest was algebra. He was a mathematician. He spent a long time in computer science and the computing industry even. I mean, he was an academic, but talking to industry people in the 1960s and 70s in Japan. But really, he's a mathematician. And so there is some mathematics in this. And there's this wonderful German warning sign that came across my Twitter feed a few months ago. And it means in German, stand back, radio control door. But it's just too good to miss. So can't tell if that worked or not. So you might get 2 slides. So Emily Riehl, who is a modern-day category theorist, has called this the Yoneda Lemma arguably the most important result in category theory. And this is the result. There's that indented 2 lines. For C, a locally small category, this collection of things is isomorphic to that collection of things with some naturality properties. And the next 2 lines give a construction of the isomorphism. So they show if you've got one of the things on the left, what is the corresponding thing on the right? And if you've got one of the things on the right, what is the corresponding thing on the left? Some work has to be done to show those are indeed sensible things in category theory, and some more work has to be done to show that those are indeed each other's inverses, so these 2 mappings do indeed form an isomorphism. But that work is not difficult, it's just sort of following your nose, following the definitions. I'm not going to do that work. My point is, it's a very compact statement of something with very few assumptions. If a category, in case you haven't thought about this before, basically it's just a collection of things and relationships between things, objects and arrows. So you might have pictures in your mind of directed graphs. So the objects are the vertices of the graph, and the arrows are the edges of the graph. You might have in mind programs, types and programs. So the objects are types, and the arrows are programs. So a program takes an input of one type and produces an output of another type. And you can compose paths in graphs if they join up, and you could compose programs between types if they join up. And those are both faithful examples of categories. You don't need much machinery. It's not such and such a sort of a yellow square funny category has such and such properties. It's a very general thing, and so it's kind of surprising that it's so powerful. You expect things that are general and have few assumptions to be very weak. They don't tell you very much because there's few assumptions to build anything on. But the surprising thing is that there's a lot built into that very small piece of mathematics. Sorry, we've got 2 clicks. roughly speaking, philosophically speaking, you might say that what the Yoneda Lemma is telling you is that a thing is completely determined by its relationships to all other things. And category theory is about things and their relationships to things. The objects are the things and the arrows are the relationships. And this is actually quite a familiar story. We have lots of examples of this. So in English we have a saying, you can tell a lot about the person by the company they keep, and I understand there are sort of Dutch and German and French and so on translations of this, many other languages too. I'm sure it's not something about British people or English-speaking people, it's something about people. In Japanese, the word for human being is these two symbols. I mean, I don't speak Japanese, I got this from somebody else. But I understand that the word for human being is these two symbols, nin-gen. Nin means person, and gen means between. And what it is to be a human being is the relationships between people. So embodied in the Japanese word for human being is the Yoneda Lemma, if you like. If you remember axiomatic Euclidean geometry from school, if you were at school several hundred years ago, then there are these things called points, there are these things called lines. Two lines intersect at a point unless they're parallel, 2 points determine a line unless they coincide. But you can tell a story about Euclidean geometry without the points because they're determined by lines, by intersections of lines. So there is nothing more to a point than the lines that meet there, which are its relationships to other points. So there's a Yoneda view of Euclidean geometry. And then you see it in the arts as well. There's a French poet, Paul Valéry, who said, I'm not going to try to pronounce the French, but it's the execution of the poem that is the poem. The poem is not just a collection of words written on a piece of paper. Thank you, there's your poem. The poem is its performance, or the collection of its performances. And just the words on paper don't tell the story. It's how it's performed, it's how it's the impact it has, the response it invokes in an audience. And similarly with music. So Theodor Adorno, a musicologist, the idea of interpretation belongs to music itself, he says, and it's not an accidental property. It's not something that's built on top of music. Beethoven's Fifth is not a collection of dots on a piece of paper. Beethoven's Fifth is the collection of its performances. It's its interpretation. It's how it's evolved over time. That's the entirety of Beethoven's Fifth. So you can understand Beethoven's Fifth by its relationships to the milieu in which it finds itself. I got those two from a big, thick book by a guy called Guerino Mazzola, called, I think, The Topos of Music, but this is a sort of 1,000-page mathematical treatise on group theory in musical scales and so on. It's really rather odd, but he picks out these examples. He talks about the Yoneda Lemma, and he also gives an example from examples in sculpture. So the piece of sculpture is not just a thing sitting there. You need to understand it from all angles in order to appreciate the piece of sculpture. You need to see it, its relationship to its surroundings, the same as a piece of architecture as well. It's necessarily a part of its surroundings. And that tells you the whole story, basically. So these are philosophical interpretations of Yoneda. Two again. But let's get more concrete. You can take as one example of a category a computational example where the objects are types and the arrows are programs. So let's say the objects are Haskell types and the arrows are Haskell programs. Then the Yoneda Lemma talks about functors and it talks about natural transformations. They have very natural representations as bits of programs. Functors, so Haskell has a type class called functor, but you can think of collection types, so lists of and pairs of and vectors of and so on. Those are all functors, collections of things. And the natural transformations are the polymorphic functions over those collection types. So something that takes a pair of things and makes it into a list of things, a list of length 2, pays no attention to the elements of the list. It works for or elements of the pair. turns a pair of integers into a list of integers, a pair of characters into a list of characters, a pair of booleans into a list of booleans, and it's completely oblivious to the contents. That's what natural transformations are. They're mappings that are oblivious to instantiations. And then if you take that terse mathematical characterization of the Yoneda Lemma and translate it into this kind of impoverished version of category theory, it might seem more illuminating. And what it says is, so here's a Haskell data type. YoFA is something with a function inside it. It's a record with one field that has a function inside it. So a record with one field, and that one field is a function. And the previous line says UFA is just the same as f of a. So when f is a functor, f of a, so f is a collection type, f of a is a collection of a's, and this is UFA is another way of representing a collection of a's. And what is this other way of representing a collection of a's? It's equivalent to, if you want to make a collection of x's, all you have to do is give it a function from a to x's. So that is to say, an f of a's is nothing more than a method for yielding a collection of x's, provided you tell it how to turn a's into x's. And I hope that seems computationally reasonable to you. Let's try it. If you have an f of a's, a collection of a's, can you turn it into this form? So if you have a collection of a's and a way of turning a's into x's, can you make a collection of x's? Well, that's precisely what the functor class lets you do. If you have a collection of a's and a function from a to x, you can map the function over the collection and get a collection of x's. Conversely, if you can make a collection of x's, let's see, which way around is this? If you can make a collection of x's given any function of type a to x, can you get back a collection of a's? So suppose you want a collection of a's and you have this black box that will give you a collection of x's, different type, provided you plug in the right a to x. What a to x do you plug in to get a collection of a's? Anyone?
X to
A. Not x to a. You've got a collection of x's, and you want to make a's. So I've said that the other way around, haven't I? You've got a collection of you've got a collection of a's, and you want to make a collection of x's. Then if you plug in, you could plug in the identity function for free, and that will give you back a collection of a's. I think I got the types wrong there, but hopefully, I mean, the program is here. The program says it much more simply than I can. So those are two mappings backwards and forwards, from FA to UFA and from UFA to FA. They are Haskell programs. I've written them as programs, so there's no more work to be done to check that they're sensible things. There is some more work to be done to check that they are indeed each other's inverses, and I encourage you to think about that. The slides will be online later. So this is a computational reading of the Yoneda Lemma, if you like. And this general pattern is there in all instances of the Yoneda Lemma. In one direction, you apply your thing to the identity thing, and you can see that's exactly what the Haskell program is doing. It's unwrapping the record to get its field and then applying it to the identity thing. And then in the other direction, you use the map, the functorial action. And those two will always crop up as the two halves of an isomorphism in the applications of the Yoneda Lemma. So conversely, if you see yourself having some data and some other representation of that data, and one direction is applied to the identity function in some way, and the other direction is map in some way, then you should suspect your little Yoneda antennae should be wiggling, and you should suspect there's an instance of the Yoneda Lemma in there. Let me give you another example. I'm going to give you a whole bunch of examples. Here's another example. So this, I said, maybe I should just use the arrows. I said here that you can turn these things into those things and vice versa. So what we've got is, so vice versa, turn an f of a's into a thing that takes an a to x's and gives you an f of x's. That's a type, and that type is equivalent to various other types using simple isomorphisms of types. So the first one is moving a quantifier, the second one is uncurrying, the third one is swapping two quantifiers, and the fourth one is turning a for all into an exists on the left-hand side of an arrow. Those are all straightforward operations. If you don't follow the operations, it doesn't matter so much. The point is, the thing at the top is Yoneda, the thing at the bottom is apparently also Yoneda. And this has been called the co-Yoneda lemma. It's a kind of dual, and this says a collection of A's is no more than a collection of X's for some type X that you don't know, together with a way of turning those X's into A's. And again, you can see if you have a collection of A's, then you can represent it as a collection of A's with the identity function. Moreover, if you have a collection of X's and a way of turning X's into A's, then you can use the map and get a collection of A's out of it. And this is useful because even when this thing is not a functor, this thing always is. So you can make a functor instance for the left-hand side when you can't for the right-hand side. Why is that important? There was a nice paper by Andy Gill and his students a couple of years ago on, they called it the remote, I'm not allowed to use this word, remote effects. You can say it. I'm not going to say the M word. Oh, there is. I have already said the monad word. So he had a little language for communicating with a device over the network. That device, in Andy's case, was an Internet of Things toaster. So you can send some commands to it. So there's a little data type of commands you can send to a toaster. You can get it to print a little message out on its LCD screen. You can get it to toast for a certain number of seconds, and you can ask what temperature it currently is. And then you might program it from bed to warm it up so that it's nice and warm to toast your crumpets in the morning. So this is a Haskell GADT. The command data type is a Haskell GADT. There's ways of making commands. A command A is a command that you can send to the toaster that returns a result of type A. So you can make a command int by using the sense command. There are commands that return ints. And you can make a command void in two different ways, the say command and the toast command. They both return void. But you can't make a command string or a command bool. There are no commands that return strings. There are no commands that return bools. So this is not a functor. Because if it were a functor, given a command ints and a way of turning ints into chars, you could make a command char. And there is no way of making a command char. And so because it's not a functor, you can't make a free monad out of it. So you can't write abstract syntax trees of programs using these things, which is what Andy wanted to do in the paper. But you can use the co-Yoneda trick, because this type here is equivalent to command R's together with a way of turning R's into A's. Command A is equivalent to command R's and a way of turning R's into A's. And this is a functor, because a thingy of A's and a function from A's to B's can always be turned into a thingy of B's, because if you've got a thingy of A's, you've got one of these, and a function from A's to B's, you just compose them, and then you get a function from R's to B's. So that's a thingy of B's. That is a functor, so you get free monads, so you get abstract syntax trees of programs, and you can go and tell the story of the remote effect thingy that Andy wanted to tell. So Yoneda to the rescue there. Here's another example, one that has lots of evidence at the bottom, which you can ignore. The important thing is the first equation there. This is a rule about less than or equal to, a rule about inequalities. B is less than or equal to A, if and only if, for all C's, whenever A is less than or equal to C, then B is also less than or equal to C. So think about this ordering here. a collection of dots. There are arrows between the dots, and the arrows mean that the thing at the tail of the arrow is less than or equal to the thing at the head of the arrow. So there's an arrow from the dot labeled B to the dot labeled A. That's illustrating the fact that B is less than or equal to A. And then the various dots labeled C, and B is below A because all the things that are above C are also above B. Conversely, if all the things that are above A are also above B, then B must be below A. This is what it is to be below. That is an application of the Yoneda lemma. And it's not obvious, perhaps, because these order things are so simple that you don't see the categories in there. But categories are things and relationships between things. Orders are things and relationships between things. Any order makes a category. It's a special kind of impoverished category. And if you just take the definition of the Yoneda lemma and translate it into terms of orderings, what you get is this well-known and familiar rule of, it's called indirect inequality, or indirect order. And this is, can be a useful way of proving that B is less than or equal to A, because you can just take arbitrary things C and prove things about them, and that turns out to be often an easier thing to do. Here's another one. There's another result about Yoneda, which I'm not going to go into the details of, but as a consequence of it, there's a similar rule about equality. Two things in an ordered set are equal precisely when the things that are above one are above the other. That's what it is for two things to be equal. They have the same things above them. Again, if you've got two equal things, B and A, then of course C is bigger than 1 if and only if C is bigger than the other, because they're the same thing. And conversely, if this for all C, then you can conclude, you can plug functorial actions in and get the other result back. I won't work out the details. Here's a third thing, and this is a friend of those in the audience. Cayley's theorem says every group is isomorphic to a particular kind of group, a group of bijections. So groups are things like transformations in linear algebra, so graphics is all about these transformations. There's a similar version of that that says every monoid is isomorphic to a monoid of functions. So every monoid is equivalent to, every monoid M is equivalent to functions, a collection of functions of type M arrow M, mappings from M to M. So if you've got a monoid, then you can certainly make a collection of functions by applying the binary operator of the monoid to one of its arguments. Then it becomes a function of the other argument, so it's a function. Those functions compose, and the identity is one of those functions. So you do get another monoid out of it. And conversely, given one of these monoids, you can apply to the neutral element and get back the original thing that you first thought of. Now, this is a standard trick in functional programming, and sometimes known as Hughes lists. So John is an expert in the Yoneda lemma from 1986 or so, and he didn't know it at the time. But there's an application to the identity of the monoid, and functorial action, which is composition. That's the functorial action of this particular functor, is there in this idea of representing lists by functions of the form x's plus plus. Those are good because list concatenation takes time proportional to the left-hand argument. It can be slow, whereas functions of the form x's plus plus can be composed in constant time, can be combined in constant time. And given one of these functions, you can extract the x's back again by applying it to the empty list. So this is what sits inside the fast reverse program, if you look at it in the right way. If you just do reverse, obviously, in the obvious way as a fold, it's quadratic time. If you represent your lists in the way John taught us, then it's just an obvious linear time program, and it's this representation that makes that work. So that's the Yoneda lemma too. So how did I come onto this? Well, I was dragged onto it by my student Guillaume, so this is what you have students for. They drag you into places you didn't think you wanted to go. But he did, and I enjoyed it. So yay for students. The ideas here come out of, they're called optics, and you might have heard about lenses. So they're compositional references to components within composite data structures. So here is a composite data structure. It's a collection of tables, and it has parts. So there's, within this collection of tables, there are some tables. And within each table, there are some fields. So within this collection of tables, there's a table EFG. And within EFG, there's a field E. And you'd like to be able to, if this is to be a compositional representation, you'd like to be able to say, within that collection of tables, I want to talk about the E thing alone. I like a reference to the E thing in the middle of my collection of tables. So how can you do this? Certainly, given a collection of tables, you can extract one table, and given a table, one table, you can extract one of its fields. So there's a getter for each component of a structure, and you can compose getters. So they're just functions, and they compose in the obvious way. But you might also want a setter. You might want to be able to write these things. So let's say you can write the E field of an EFG record, and you can write the column vector thingy inside an oval. How do you write the E thing inside an oval? Well, you can. It takes a little bit of thought. It's not quite as straightforward as composing the getters, but to write the E thing inside an oval, you get the column vector out of the oval, you write the E thing in the column vector, and then you write the column vector back into the oval again. So a three-step way of manipulating the E things within ovals. So those are called lenses. There are sources and views. You can get a view from the source, and given an updated view, you can get the old source and the new view, and you get a new source out of it. So these were popularized in functional programming by Nate Foster and Benjamin Pierce, and this work on, they called them lenses. But the ideas are much older than that, so there's some stuff on actually categorical representations of memory, stack frames in memory from the 1990s and 1980s, where these ideas are also there. So a stack is a collection of stack frames. A variable is stored inside a frame, inside the collection of stack frames. How do you talk about that compositionality? So we can represent these things as pairs of functions, as getters and setters. So here I've called them the getter and setter, a view and update for a lens. From a source, you get a view A. You can update that view A to a different view B. And then you can put that different view back in the source, and then you get a new source T. So think about, let's say, pairs and their left-hand component. You can project out the left-hand component of a pair. You can change it into some new value and put it back in, overwriting the left-hand component, the old left-hand component of a pair, to get a new pair. There are also ways that this is a way of viewing a component of a product type. A pair is a product type. There's a dual, which is viewing components of a sum type. So if something is either one thing or another thing, you can get it as one of its variants, do some stuff on it, and put it back into the sum type again. And if it's not one of those variants, then there's nothing to do. So if you have an optional integer, you can increment it by getting the integer if it's there, incrementing it, and turning it back into an optional integer again. They turn out to have a common specialization, something that's both a lens and a prism, and I've called that an adapter. So this is a lens where the view contains all the information. So when you put back a new view, you don't need the old source to reconstruct a new source. The new view tells you everything there is to know, so you can just discard the old source. It's also a prism, a sum type, where there is only one variant. So there's no choice when you're downcasting to see whether you can do something. You always win. And so there's no choice in this matching function. So Benjamin Peirce and Nate Foster's work on lenses use this concrete representation. A lens is a pair of functions. And this is OK, but it's a bit clunky to compose them. You can do it. However, you can't combine a lens with a prism. So if you have a field inside an optional record, you can't always get the field because it might not be there. The record's an optional record, and you can't always set because you need some other, you can't always, so it's not a lens, and you can't always build because you need more information than just the field to do so. So the combination of a lens and a prism is not a lens, and it's not a prism, and it doesn't fit within this terminology at all. So that's a bit sad. You can compose lenses with lenses, and you can compose prisms with prisms, but you can't compose lenses with prisms. So there's this funny, fancy, clever representation in terms of these things called profunctors, hence Profunctor Optics. What's a profunctor? It's like a functor, but more so. So it's a two-argument functor. So a functor of an f when f is a functor, think of it as a collection of a's. You can get some a's out of it. A profunctor takes two arguments, so p, a, b. You can get some b's out of it, but you can put some a's into it. So it's like a transformer that turns b's that you can put in, sorry, a's that you can put in to b's that you can get out. And whereas functors have an f-map operation, so you can map over a collection, profunctors have a die-map operation that says if you can turn a's into b's, and you've got a way of turning c's into a's and a way of turning b's into d's, then you can stuff some c's in, turn them into a's, put them through the transformer, get some b's out, and turn them into d's. So that's the functorial action of profunctors. Formally, they're just functors on products of opposite categories and stuff, but you don't need to know that. So now, the clever thing is, you can represent an adapter, which was this degenerate lens and degenerate prism. It's a pair of functions, one from S to A and one from B to T, which is very like what die-map does. It takes a pair of functions, an S to A and a B to T, and sort of wraps them around. It turns out that there's another way of doing adapters, which is precisely what die-map does. It turns PABs into PSTs. Now, why? How does that work? What's going on here? Think of an adapter in this concrete way as you've got S things and you want to operate them on them as A things, so you have to change their format somehow. Maybe these things are A, B, C triples, and what you want is A, B, C nested tuples. So you've got some library functions that work on nested tuples. You've got a triple. You need to turn your triple into nested tuples, do the library function stuff, and then turn it back into a triple again. That's what this adapter lets you do. And this says, well, if you've got any way of turning your A's into B's, then this is a way of turning S's into T's. You turn your S's into A's, you do the library stuff from A's into B's, and then you turn the B's back into T's again. So it's the same picture that's going on, really. But it's a natural operation on profunctors. In fact, it's the functorial action of profunctors. And the remarkable thing is two remarkable things. One is that the same works for lenses and for prisms. It's just a different type class constraint here. And the other is that now an adapter is just an ordinary function, a single ordinary function, not a pair of functions. And the profunctor representation of a lens is a single ordinary function, not a pair of functions. So they're just composed like single ordinary functions compose. They compose nicely. Moreover, single ordinary functions with a type class constraint, if I've got a single ordinary function with one type class constraint and I want to compose it with a single ordinary function with another type class constraint, I get a composition of single ordinary functions with two type class constraints. The type class constraints just conjoin. You need this property and you need that property. So the fancy representation of lenses composes with the fancy representation of prisms and makes a fancy representation of lensy prismy things. But you can express lensy prismy things in this format. So that's quite remarkable. and very short and sweet, but quite mysterious as well. And what's really going on here? In fact, I've shown you one definition of adapters as a pair of functions. I've shown you another definition of adapters as a single function with some funny type class constraint. Are those the same? Indeed, turns out they are the same. They're in fact precisely isomorphic. And the reason they're precisely isomorphic is, surprise, surprise, the Yoneda lemma, used twice. So this is a result that's due to Bartosz Milewski, who's a very enthusiastic blogger on functional programming and category theory. So I credit him with the idea, the observation. If you just do two applications of the Yoneda lemma, you get that thing on the top line in red. That might not be very enlightening, but let me say it in Haskell, where I instantiate these categories to Haskell and functors to Haskell functors and arrows to functions and so on. This says this type on the left is precisely equivalent to that type on the right, which is to say, if you've got a mechanism for turning a collection of A's into a collection of B's and it works for any collection type, then what you have is nothing more, nothing less than a function from A's to B's. Why is that? Well, if you have a function from A's to B's, then you have a way of turning any collection type of A's into a collection type of B's. You just use map, the functorial action. Conversely, if you have a way of turning a collection of A's into a collection of B's for any collection type, you use the identity collection type. And that is a way of turning an identity collection of A's into an identity collection of B's, a single A into a single B. So that's just a function from A's to B's. So one direction was the functorial action, map, and the other direction was applied to the identity, here the identity functor. And these are the two mappings, backwards and forwards between those two types. They're very short, they're very sweet. One is use the identity, one is use the functorial action. You have to do a little bit of work to show that they are each other's inverses, but again, that's not difficult to do. And this works in any category because it uses none of the, Yoneda lemma had very few assumptions, so this works for any assumptions. So it works not only for adapters, it also works for lenses and for prisms. So the concrete representation of lenses as a getter and a setter is indeed isomorphic to the profunctor representation of lenses. The concrete representation of prisms is isomorphic to the profunctor representation of prisms. But more, these profunctor representations are much more compositional than the record of two functions representation is. And that's all I wanted to say. Yoneda lemma is my new favorite thing. It's essentially very simple because there's so little there, how could it be anything other than very simple? But surprisingly deep. It has lots of applications, it's all over the place, and as Emily Reel said, it's arguably the most important result in category theory. There's so much embodied in that little equation. Before I found out about Yoneda lemma, I had another paper on Profunctor Optics, which had much more complicated proofs of the equivalence of these two things, and they were my previous favorite thing, Profunctor Optics. So they are a clever representation, higher order because representing things as functions, higher kinded because they're parameterized by profunctors, which are a type class constructor, nicely compositional, powerful, not obvious, mysterious where they come from. And I had some long-winded proofs about it, but they're quite nice as well. The lenses are good and profunctor optics are better. And they put my previous favorite thing and my new favorite thing together, and the new favorite thing answers some of the problems with the previous favorite thing. The proofs just become way shorter and sweeter and easier to follow and more believable. So lots of people contributed to this. My student Matthew Pickering was the one who got me into lenses in the first place. Well, that's not true. Got me into Profunctor Optics in the first place. And this work is based on an ICFP paper with Guillaume, which you can get from my webpage. And just a last-minute plug, I'm also here representing the software engineering program, a part-time professional master's program at the University of Oxford. We don't have courses on the Yoneda Lemma, sadly, but we do have lots of interesting courses, including functional programming taught by me and concurrent programming taught by Francesco Cesarini, and lots of other exciting stuff. I have a table. Come and have a chat to me. I'll be very happy to talk.
So I'm going to have to ask the first question. Doesn't the existence of co-Yoneda imply that you actually don't need a lemma? Sorry. Any questions?
Not going to answer that one.
So that was perfectly clear then. Good.
Blinded by science. There will be a test on the way out. There's a little smartphone with a test on the way out.
All right, next talk's at 14:30, and Simon Baton-Jones will be in the big room. Just figured you might need to know.